So bonjour.
Thank you very much.
Thank you. Bonjour, and of course let me thank the organizers and especially Luca for the invitation. It's a real pleasure to be here. Actually, this is something I planned since the very first edition of the Journée sous-riemannienne, but unluckily this is teaching time in Italy, so I was never able to come here. I'm very happy that this year I managed to come. So as you see in the title, I will speak about these rectifiability issues. I will be more precise in a moment. In sub-Riemannian geometry, actually this sub-Riemannian geometry is kind of fake because the setting will always be Carnot groups. Oops.
Cancel. No,
Okay. So my plan is to start with by introducing Carnot groups and the notion of intrinsic Lipschitz graphs in this setting, and then later I will deal with the two rectifiability issues I want to discuss, namely the rectifiability problem for sets with finite perimeter and the Rademacher theorem for intrinsic Lipschitz graphs in the more restrictive setting of Heisenberg groups. Okay, so let me start with the definition of Carnot group. Of course, this audience is very well educated on the subject, so probably I will spend some time on it, but probably it's unnecessary. A Carnot or stratified group is a Lie group which is connected, simply connected, and nilpotent. This means, of course, that it's diffeomorphic to Rn. With the extra property that its Lie algebra admits this stratification. It can be decomposed into direct sum of several layers, G1, G2, Gs, right? With the property that the bracket between an element in the first layer and an element in the I-1th layer gives you an element in the ith layer, okay? And the last layer commutes with G1 and so with all the algebra. So the last layer is in the kernel of the algebra. Good, so just only to justify the sub-Riemannian geometry appearing in the title, why are we interested in Carnot groups? We are interested in Carnot groups because, as you know, they are the infinitesimal, the tangent models, the local models of sub-Riemannian manifolds. So a smooth manifold endowed with some bracket generating a smooth subbundle D, on which you put a metric G, which measures horizontal vectors in the horizontal bundle. Okay. Also, this slide is pretty useless in this this audience, but let me show it to you anyhow. We will always think of G as identified with some Rn. As I told you, they are diffeomorphic by assumption, with exponential coordinates. And these exponential coordinates are associated with a so-called adapted basis of the algebra. So we start by fixing, this is the basis of the algebra that we choose to construct exponential coordinates, and it's done in such a way that we start by listing some elements which form a basis of the first layer, then we list a basis of the second layer, and so on. Okay? Then we have dilations, which through this identification reads as follows. So on the ith layer, well, on the jth layer, a dilation times a factor r acts like r to the power dj j times the coordinate. So on the layer dj, the dilation acts as a multiplication times r to the degree. Okay. And then, So from time to time, distances and balls will appear, and even this norm will appear. This is one homogeneous norm that you can fix, homogeneous with respect to dilations. Okay. Actually, it's not a norm, it's just a pseudo norm because it satisfies the triangular inequality only up to a constant greater than 1 in principle, but it's just a reference norm that you can fix. Of course, it's equivalent to the Carnot-Caratodori distance, and you can, when speaking about distances and balls, I will mean the left invariant distances and balls associated with such a norm. You can consider any equivalent norm you like, for instance, the Carnot-Caratodori one. Okay, now something which is maybe a bit new, more new than what I told you up to now, intrinsic Lipschitz graphs. Okay, assume your Carnot group is decomposed in this way, as a product WV of subgroups which are homogeneous, so invariant with respect to dilation. Actually, some extra properties are required. Let me hide these technicalities. Okay, so imagine you are given this splitting. So your Carnot group is decomposed as a product of two subgroups, W and V, which are complementary. So, okay, they generate all the group and say that their intersection also is just the identity. Okay, the typical case is, of course, when your group is Rn and you decompose it into the direct sum of Rk and Rn minus k. Okay, and imagine you are given a map phi from W, the first subgroup, to V, or from a subset of W to V. We define its graph in this way. So it's the set of points of the form elements in the domain of the function times the function itself evaluated at the element. Okay, so when you are considering this splitting, right, and phi is a function on Rk with values in Rn minus k, this is the classical notion of graph. Okay, it's not working. This is the classical notion of graph of a function from Rk to Rn minus k. It's a subset of Rn. Okay? And we want to speak about Lipschitz continuity for such maps from a subgroup to another. And the notion of Lipschitz continuity for such maps is introduced in terms of comparison with homogeneous cones. Okay? So let me introduce the cone. So by this I mean the cone with vertex, the identity of the group, and aperture alpha is the set of points of the form element in W times element in V, with the property that the norm of the element in W is bounded by a constant times the element of V. So you have to imagine this guy as a cone. So of course this is a one homogeneous cone. It's homogeneous with respect to dilations because the norms we considered are homogeneous. Okay, you have to imagine this guy as a cone with vertex the origin with axis V, right? All elements in V, of course, belong to this set because they are of the form identity times V, and the identity is norm 0, right? So it's an open cone around V with axis V. Okay, and alpha is an aperture parameter. So the smaller alpha, the smaller is alpha, the smaller is the cone. Okay. And the definition of intrinsic Lipschitz continuity for for a map from W to V is given in terms of this cone. So we say that phi is intrinsic Lipschitz if the graph of phi, that I introduced there, enjoys this comparison with cones property, right? So when I pick a point in the graph, right, and I look at the cone now with vertex P, so I left translate the cone to the point P, and I intersect it with the graph of phi, then I get just the vertex itself. If you think to this example, this comparison with cone property gives you precisely the notion of intrinsic Lipschitz continuity for maps from Rk to Rn minus k, right? Because these cones are standard Euclidean cones around Rn minus k. Let me also say that in general phi is no better than Hölder continuous and the Hölder continuity. So when you identify W with some Rn, Rk, phi in general is no better than Hölder continuous, and the Hölder exponent is 1 over the step of the group. So in general we have no good no immediate regularity property for such graphs. Okay, so let me come to the first of the two rectifiability type issues I want to discuss. So the first one is related to the problem of the rectifiability of sets with finite perimeter. So we say that a subset E of G has finite perimeter if the horizontal derivatives of the characteristic function of E in the sense of distribution, so the derivatives with respect to the left invariant vector fields in the first layer are represented in the sense of distribution, this is a distribution, by a finite measure which is vector valued. By finite I mean a vector valued measure with finite total variation. Now the total variation of a vector valued function is a positive measure, and we want it to be finite or locally finite at least. In this case we will say that the set has locally finite perimeter. And the perimeter of E is the total variation, this is a positive measure of such a vector valued measure. Okay, so now by Reed's or whatever theorem you like, this vector valued measure can be written as this scalar measure, the perimeter, times a unit vector valued map that we denote by nu E, and which is what's called the measure theoretic horizontal normal to the set E. You have to imagine this nu E as kind of the unit normal to the boundary of E, which is pointing inside E. Okay, it will be relevant for us the notion of reduced boundary of E. So the reduced boundary, that I will denote by this symbol, is the set of points P where the following limit exists. So now this is a vector valued measure, and we measure it inside the ball of radius P, of center P and radius R. Right? This is a vector, and we divide it by this number. Right? This is a positive scalar measure. So the perimeter inside the same ball. Of course, in norm, the norm of this vector is less than this number. So this is a vector with length less at most 1. Okay. We are asking that the limit as r goes to 0 of this vector is precisely the normal, so this measured theoretic normal evaluated at the point P. Okay, so in a sense, we are considering the set of points where, so since this measure is normal times the total variation times this scalar measure, we are kind of asking, we are kind of selecting the points where at small scales, for small r's, are okay. At small scales, the normal here, so imagine here we wrote normal times this measure. The normal is almost constant, does not vary very much, okay? So we are selecting points where the measured theoretic normal is almost constant around the point. And this set, the reduced boundary, is relevant for us because by a much more general result by Luigi Ambrosio, it is possible to write the perimeter as, and so also the derivatives of the characteristic function as an Hausdorff measure up to some multiplicity, an Hausdorff measure on the reduced boundary, restricted to the reduced boundary, okay? Where the dimension of the Hausdorff measure is a one codimensional measure, okay? So Q is the homogeneous dimension of G, and the Hausdorff dimension is the one associated with dimension Q minus 1. Okay, so following the George approach to this problem in Euclidean in Rn, there are at least two natural conjectures. So the first one, the one I'm interested in, is I call it R, which stands for rectifiability. So we would like to prove that the reduced boundary is rectifiable. Rectifiable means that up to negligible sets, negligible with respect either to the Hausdorff measure or with respect to the perimeter, your choice. Up to negligible sets, the reduced boundary is contained in a countable union of intrinsic Lipschitz graphs. So the graphs of countably many phi's, where these phi's are defined on objects. So our graphs of codimension 1. So our objects are graphs of maps defined on with values in a one-dimensional group and with domain which is a maximal vertical subgroup of G. Okay, so VI can be written in this way. Okay, so this is the rectifiability conjecture we are interested in. Actually, there is a second conjecture, which would be very interesting. I called it B, which stands for blow up. We would like the following. We would like that at any point of the reduced boundary, when you consider the blow up, so pick your point, translate it so that P goes to the origin, dilate it. We would like this blow up to converge to something which is a half space. A half space which has to be orthogonal to the normal. So this is what happens. So imagine a smooth set, right? When you fix a point on the boundary, you have the inner normal to the set, you blow it up, you get, so the set is converging in L1 under blow up to precisely to the half space which is orthogonal to the normal. Okay, so these are the two problems we would be interested in. I will say something new only about the first one, the rectifiability property. Let me just briefly tell you some known result. So this H should not be here, but both problems, rectifiability and blow up, are solved, are settled in Carnot groups of step 2. This was done by Franchi, Serapioni, and Serracassano a few years ago, and also in these clubs, so groups of type star, which was, so I don't want to introduce this class, but this was introduced by Marchi a few years ago. And actually, a C1 version of the rectifiability theorem holds, meaning that here the reduced boundaries contain, it can be proved it's contained almost everywhere in a countable union of graphs which are not only intrinsic Lipschitz but intrinsic C1. Okay, but so this is what I mean that by saying that a C1 version of R holds. Actually, it's also known that a blow-up property cannot hold in general. And in fact, in the Engel group that I'm going to introduce in a while, one can produce a set E which has finite perimeter which is a cone. 0 is in the reduced boundary, the identity is in the reduced boundary, but E itself is not a half space. So for this set you have a point in the reduced boundary, the identity, where, the set itself is a cone. So when you blow it up, everything stays fixed. So it converges in L1 to itself, and it's not a half space. Okay? So there is a set where this blow-up property does not hold. Of course, actually, the real conjecture one would be interested in is an almost everywhere blow-up property. Okay, so what happens in Rn is that at all points of the reduced boundary, the blow-up to a half space holds. So the blow-up convergence to a half space holds. Actually, we would be happy if this were true just almost everywhere. And this is open. So in this version, in this more precise version, the problem is open. There is only the only general result, even though only partial I am aware of, is due to Ambrosio, Bruce Kleiner, and Enrico Ledonne a few years ago. They proved that at almost every point of the reduced boundary, there is a sequence of scales according to which the corresponding blow-up converges to a half space orthogonal to the normal. But this is true only at some selected scales. So the full problem, convergence of the blow-ups, is open. Okay. So we are not sure, we cannot guarantee that the blow-up is unique. So if it were unique, we would be done because we have a sequence where we have convergence to half space. Okay, so I want to present some new result which hold, for instance, in the Engel group and actually in a wider class of groups. So, but let me introduce the Engel group. As you know, you probably know, it's is a four-dimensional Carnot groups associated with, for instance, this algebra. So the first layer is two-dimensional, generated by x1 and x2, whose bracket is x3, the generator of the one-dimensional second layer. And then x1 and x3 generate x4, which is the generator of the third layer, while x2 and x3 commute. Okay. And what we were able to prove in collaboration with Sebastiano Donne, which was my PhD student, Enrico Ledonne, and this PhD student, Rimo Isala, is a rectifiability property in the Engel group. So we are able to show that for every set with finite perimeter in the Engel group, almost all of the reduced boundary is contained in a countable union of intrinsic Lipschitz graphs of codimension 1. Okay, so before giving you some hints, some flavors of the proof, let me state a couple of remarks. So, as I told you, this is something which we are able to prove not only in the Engel group, but in a more general class of Carnot groups. Precisely, it's a class of groups where at least one horizontal line, so exponential of tx for a horizontal direction, fixed horizontal direction x, is not abnormal. Okay? Actually, this is a purely algebraic condition on the algebra. So you give me the algebra and its relation, its brackets, and I'm able to tell you whether this algebra and the associated Carnot groups falls into this class. So there is at least one horizontal line which is not abnormal or not. So our condition is purely algebraic. The second remark is that the blow-up property would follow from a rectifiability property in case we had at our disposal a Rademacher theorem for intrinsic Lipschitz graphs in the Engel group, and this is not available. So if we were able to prove that intrinsic Lipschitz graph of codimension 1 in the Engel group are satisfy a Rademacher theorem, so almost everywhere you blow them up, you get a subgroup, as we will see in a moment. Then, from the rectifiability property, we would most likely be able to prove also the blow-up property.
Sorry.
Yeah.
Do you know when all horizontal lines are abnormal?
Yes. I mean, that is a purely algebraic condition.
So give an example. Easy example.
Okay, so all, I would say that all step 2 free groups are such that starting from rank 3 probably are such that all horizontal lines are abnormal. So they do not fall into our class. I must say, I believe that generically a Carnot group does not fall into our class. But from this respect, you are much more expert than I am. Yeah, actually, I mean, you can construct.
No, 235. 235 is an easy example where all lines are also abnormal. Okay. They're not strictly abnormal, but they're abnormal. And the example where there's at least one, for example, is Bursa. All Bursas, they just have one singular direction.
Okay. So let me give you some ideas from the proof. It's well known to experts that, remember, we are picking a point at the reduced boundary, we are blowing it up. There might be several different blow-ups, okay? But all of them will contain the following object. Okay, so before discussing the object, you have to think in this terms. So when you blow a set up at a point of the reduced boundary, you are converging to a set, so maybe up to subsequences, you will be converging to a set. That set will have a constant horizontal normal. So it will have finite perimeter and its measured theoretic normal will be constant. Now, this set is kind of the smallest possible set among all those with finite perimeter and constant horizontal normal. And this set, I denoted it by S nu E, P, so this is the normal. So this set is defined in terms of the normal, of this fixed unit vector. It's the semi-group generated by these elements. So the idea is the following. So this set is the set of points that you can reach from the identity by following either directions which are normal to the normal, orthogonal to the normal. So imagine that on the first layer you put some scalar product you like. Okay, so now you do the following. So you start from the origin, and you look at the points you can reach by horizontal curve, which go either in a direction orthogonal to the normal or in the positive direction of the normal. Okay. This is a semi-group because it's closed by multiplication, but it's not closed. It does not contain the inverse of their points. So an interesting point is that either in Carnot groups of step 2 or of type star, the semi-group is the half space associated to the normal. So basically you are done, because the blow-up contains the half space. Actually, if you blow the complement, you see that the complement must contain the complementary half space. So the only possibility is that the blow-up is the half space itself. But for instance, in Engel, in general, there is a it might happen that the semi-group is less than half space. For instance, for the cone I told you about before, which is actually the semi-group associated to the horizontal, to the abnormal direction in Engel, I believe. What happens is that the semi-group is smaller. But now all blow-ups contain this semi-group S. This means that if you look at your blowing up objects, right, at a fixed scale, say at scale 1, then your blow-ups are forced to invade all of the set, all of the semi-group, because they have to cover it in a measured sense. So the measure of the part of the semi-group inside the ball which is not covered by the blow-up is going to 0, is infinitesimal. Now, our assumption implies the following, so here you have to believe me. The semi-group contains in its interior a horizontal half line associated to some horizontal direction y bar, which, fun fact, might be different from the normal, from the direction you were fixing at the beginning. So usually when I imagine this set, right, I'm allowed to travel along the positive direction nu, and then along orthogonal direction. So I would imagine the cone to be an open neighborhood of this horizontal normal. Actually not. The horizontal normal might stay on the boundary of this set. Nonetheless, our assumption allows us to say that some other horizontal direction, y bar, is contained in the set. And now, I'm stating something which is easier to prove, so if you think a bit about it, than to state. So it might seem pretty mysterious, but exercise, try to think about this. So if the normals, all the normals to the set at points of the reduced boundary were close enough means that they do not vary too much, and so probably you can imagine this semi-group will not vary too much. And if it doesn't vary too much, you can imagine that there is a fixed direction, y bar, which is horizontal and contained in the interior of all the possible semi-groups associated to all the possible normals. So assume that all the normals are close one to the other. And assume that this convergence is uniform in P. Then it's fairly easy to prove that locally, up to a localization argument, the reduced boundary is contained in an intrinsic Lipschitz graph of a map which goes in the direction y bar, which is the direction which was in the interior of the cone. The idea is that, okay, you have a point where your blow-ups cover almost all of a cone. Pick another point, right? If, okay, so this cone contains the, oh, maybe it's better to use blackboard. Oh, thanks. So pick a point P in the reduced boundary, okay? There is a cone with some horizontal direction in its interior. So pick another point Q in the reduced boundary. So we want to prove that Q cannot be here, for instance. If it were here, then we will have another cone with the same direction in the interior. And now what happens? The following happens. So we have this convergence, which means that, and it's uniform. So we can imagine that locally around P, the set in the blow-up, the set is covering almost all of this cone. Okay, and now imagine that the scale where I draw this ball is much larger than the distance from P to Q. So this picture is not feasible because if you perform the same argument on the complement, you will have a complementary, so an opposite half cone, where here, right, the set can cover almost nothing, right? Because the complement will cover almost everything. But now, if you put things together, you are saying that. So since the blow-up at P contains almost all of this cone, it also contains almost all of this set, right? But if you perform the blow-up here, you are saying that the complement is covering almost all of this cone, opposite cone, and so almost all of this part here. So what I depicted here should be at the same time covered 99% by the set and 99% by its complement. This is not possible. Okay, so okay, here we are. So that's what I wanted to tell you about the rectifiability problem for sets with finite perimeter. How much time do I have?
Good question. 15 minutes, a little bit less.
Okay. Okay, thank you. So the second problem, sorry? The second problem I wanted to discuss concerns a Rademacher theorem for Lipschitz graph now in the very restricted setting of the Heisenberg group. So as you know, it's the nth Heisenberg group, Hn, is something which is 2n plus 1 dimensional. Its Lie algebra has a first layer, horizontal layer, which is 2n dimensional. The second layer is 1 dimensional, and you have generators x1, xn, y1, yn, which satisfy this relation. And so xj bracket yj gives you t, and if you commute two x's or two y's or xj with yk, you get 0. So in coordinates, that's there I wrote the group law, the left invariant vector fields, and dilations, but we can forget it. So the problem we are interested in is the Rademacher theorem for intrinsic Lipschitz graph, so which can in principle be stated for any group given a splitting of the group G as W times V. So remember, we are interested in intrinsic Lipschitz functions from a subgroup W of G to a complementary group V. We say that phi is intrinsically differentiable at a point W of the first subgroup W if the following happens. So pick the graph of phi, translate it so that this point, this is a point on the graph, right? W is the point you are of W, capital W, that you are considering. So translate this point, translate the graph so that this point goes to the origin and dilate it. And you would like this blow up to converge to a subgroup of G. Actually, so here I was a bit sloppy. It should be a subgroup which is kind of isomorphic to W, to the domain, okay? So when you consider the splitting of Rn as Rk times Rn minus k, you would like the blow up of the graph to converge to some Rk. Good? So, and the Rademacher problem asks whether an intrinsic Lipschitz function phi is differentiable, is intrinsically differentiable, so in this sense, almost everywhere on W. This mu W is either the R measure of the group W or whatever Riemannian measure you put on it. I mean, W will be a nice, smooth submanifold of G. Okay. And we want to discuss the simplest case in which G is the group is the Heisenberg group. Okay, so what's known is that the Rademacher theorem for intrinsic Lipschitz graph holds either when for low dimensional graphs. So when the dimension of the domain W is between 1 and n. This is, so in this case W is, okay. The relevant case is when W is a horizontal subgroup, so a abelian subgroup of the Heisenberg group. And this exists, so such a W exists only if its dimension is at most n. Actually, in this case, the Rademacher theorem is easy because graphs from such a W to the complementary V are Euclidean Lipschitz, and so they are rectifiable. The other case when a Rademacher theorem is known is when is the case of graphs of codimension 1, right? This was proved a few years ago by Franchi, Serapioni, and Serracassano. So when W has dimension 2n, then it has to be a vertical subgroup. This is the topological dimension, okay? So it must contain the direction t, and then it's a hyperplane in Heisenberg. So in this case, a Rademacher theorem is known, and the reason is that an intrinsic Lipschitz graph will separate your space into two regions, each of which has a finite perimeter. And in the Heisenberg group, you have a blow-up property for sets with finite perimeter, and this blow-up property is intrinsic differentiability for such graphs. So what's open is these cases. So it's the case of graphs of codimension k between 2 and n. Okay? So this is what's left open. So the situation we are interested in is when W is a vertical subgroup of the Heisenberg group of codimension k. And V will be a subgroup which is horizontal, abelian, and so it's isomorphic to Rk. Okay, so what I'm able to show actually is this partial result when in the second Heisenberg group, so this is, and K, I'm able to prove a Rademacher theorem for graphs of codimension 2. So this is the very first case which is open according to this slide, right? K equal 2 and E equal 2. So in H2, when you consider a splitting W times V, where W is vertical and three-dimensional, and V is horizontal and two-dimensional, then any intrinsic Lipschitz function from W or a subset of W to V is differentiable almost everywhere. So almost everywhere, the blow-up of the graph is a subgroup. Okay, as a almost immediate consequence, in this case, so when you are able to prove a Rademacher theorem, you basically also have an area formula for such graphs. So you can recover the Hausdorff measure of the graph of the function as an integral on W of something, some area element. And also losing type C1 approximation theorem. So every intrinsic Lipschitz function phi can coincide with a function which is C1 almost everywhere out of a set of arbitrarily small dimensions. So you give me epsilon, I can produce, and a intrinsic Lipschitz function phi, I can produce you another function which is intrinsic C1. Let me skip the definition of intrinsic C1 regularity, and agrees, it coincides with the given phi out of a subset of measure epsilon. So there is no way I can tell you how the proof works. Let me just mention that it heavily uses the language of currents, and in particular the complex of differential forms in the Heisenberg group introduced by Riemann in '94. So Riemann was able to introduce an exact complex of differential forms in any contact manifold, actually, so not only in the Heisenberg group. So when you have such a complex, you can define currents by duality. And using this language, so a current is kind of a generalized surface, right? And with this language and a lot of efforts, one can prove this, the previous results. So rather than speaking about the technique I used, I believe it's better to introduce other useful tools which have an independent interest. And actually I was able to prove, so the two results I will state now hold not only in the Heisenberg group but in any Carnot group G when the splitting is W times V is such that V is isomorphic to Rk. So V is a horizontal subgroup, and this implies it's abelian, okay? So in particular, this holds in the situation that we are considering. So the first theorem is an extension result for intrinsic Lipschitz maps with values in V, okay? So this is not immediate. When you have a function which is defined only on a subdomain of W, it's not trivial to prove that it can be extended to a Lipschitz function on the whole of W, okay? But this is true. Possibly you lose something, so the Lipschitz constant has to increase, but this is not a problem. So this was proved, this was already known in the case of codimension 1 graphs, so when V is R. I proved it a few years ago, and then later Franchi and Serapioni were able to give a different proof. And the second tool that is useful for proving the Rademacher theorem in the Heisenberg group is an approximation result. So I'm able to prove that for any intrinsic Lipschitz function phi from W to such a V, there exists a sequence of smooth intrinsic Lipschitz functions, with bounded intrinsic Lipschitz constant, uniformly bounded in I, which converge locally uniformly to your given function. Okay, so since there is no way I'm able to speak of the general strategy of the proof of the Rademacher theorem, I prefer to state something else which seems to me being of independent interest, and that's all I wanted to say. Thank you.
Okay, thank you.